Okay, I think we'll get started. So today we're going to talk about the Two Slit Experiment. This will complement our discussion from last time regarding hydrogen. And we saw that as we went from the solar system model that failed to lead to a stable hydrogen, then Bohr comes along with the Bohr model and these special orbits appear. And then those special orbits appearing suggests that electrons should behave as neither particles nor waves, but have a manifestation of either in this wave-particle duality. Well, the two-slit experiment is an experiment that really exposes that behavior. So let's imagine here we've got this electron gun that will fire one electron at a time. Okay. So we fire one electron and we get a little hit over here on, say this is some kind of phosphorus screen or something. And we record that hit, that position. The fact that it hits right here looks like it's in that case, it's manifesting its behavior as a particle. So the presence of this detector here causes the electron to appear in one spot. Okay. We fire another electron here, 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 here. Okay. And as we fire millions and millions of electrons and start to look at the distribution of the electrons here, we see a distribution that peaks in the middle and actually looks precisely like a two-slit distribution for an incoming wave. And so we see the wave-like character manifesting itself in the distribution, the probability distribution of where these electrons hit on the screen. And so to describe that, we say that as the electron passes this wall with the slits, its behavior is manifestly wave-like. And so it passes through both slits at the same time and interferes with itself, just like a light wave passing through two slits or a water wave passing through two slits. But then, when it interacts with the phosphorus screen, it manifests itself as a particle. So this is the result of just doing this experiment. Now let's tweak this experiment just a little bit. So I'll redraw this. Let's redraw it. And so I'll put the slits back up. And our screen. Now we'll fire our electron, but we'll add one more thing to this. We will monitor the slits, or one of the slits. We could monitor both, but all we need is one here. So now what we'll do is we'll fire an electron and we'll record its position, right, where it hits, but we'll also record whether or not this detector fired. So this is connected to a computer. We press the button, fire an electron. If this registers, then we know the electron went through this slit. If it doesn't register, we know the electron went through this slit. So everything else is the same, but we start to fire a bunch of these electrons. And after we fire millions and millions of these, we build up a probability distribution of where they're hitting that looks like this. Peaked right behind the slits as if we were firing little BBs or bullets through the slit. And we get just this. Most of the distribution occurs right behind the slit. And so the simple act of watching or determining which slit the electron goes through changes whether it behaves as a particle or as a wave. And so there's a lot more deepness we can go here. We're going to save that for the quantum mechanics course after this sequence of 3 introductory courses. But we are starting to learn about electrons, and electrons have these wave and particle-like character. So I wanted to go through this to just give you an outline of the experiment. And so, yes, the electron can behave at times like a particle, at times like a wave, and it depends on the nature of the experiment as to whether it behaves as a particle or as a wave. All right, just to kind of solidify some ideas, let's push this a little bit. Let's fire an electron now in a 3-slit experiment. Okay, well, if we don't monitor any of the slits, then it manifests in a wave-like case as it passes the wall with slits. Again, the phosphorus screen is always going to register just as if particles, but the distribution of where they land will be this interference pattern. And this will be a pattern that's more complicated than the 2-slit. Maybe something like that. Right? So it'll be an interference with 3 waves. Now let's change this a little bit. Let's say we monitor the top slit. Now when we fire an electron, either we'll register it goes through here, in which case it will be acting like a particle, and we will get a buildup right behind this slit. Or we don't register, and it will be acting as if it's going through a 2-slit. See, we won't know which one of these 2 it went through, so it will go through both of those, but not this one. And we will get a distribution like that. And so overall, we will get something that looks like that, the combination of a single slit and the double slit. Okay. All right, so that's all we really need to know about this for this course. And again, the key message is that this is that of this wave-particle duality that the electron carries, all particles for that matter, but only when things get down to the size of an electron does it really matter. We do see some things in chemistry, certainly, where the wave character of a proton matters. That can affect some kinetics and other things in a reaction, but and just the nature of how hydrogen is distributed in a molecule. But by and large, we can treat atoms, full atoms, as particles for the most part. It's only the electrons that we really do need to acknowledge their wave-like character to truly understand chemistry. And essentially, what we'll see is that to form bonds, we're overlapping these this distribution of the electron through space. So it's more of its wave-like character.